So, welcome to this awesome talk about FlameGraph. First, how many people have heard about FlameGraphs? That's already something, let's see together what we can do. Okay, I work for Red Hat in the messaging team, and the point of view I will give you about this presentation is the same point of view of a user of this kind of tools, this kind of stuff related to profiling. That's very important. And specifically for my job, we really care about performance. So it's something that we really care of. Let's dig together into that. First, someone has told me that they didn't know what FlameGraphs are. Okay, it's a kind of a way to visualize profiling data. Nothing more, nothing less. Okay, so we start from a program, and I will show you what a flame graph of it will look like, and we learn together how to read it. So the program is quite simple. We have a main that is not here because I wasn't having space on the slides, that is calling continuously A. The method A is calling B, so it isn't doing anything more. And B on turn is calling C, D, and performing some EV work. So we don't have here the code, but EV works is doing something inside of B. Then C and D are both performing EV works, and specifically D is performing EV works twice. Okay? You don't have to remember by heart this, because it's here. Okay, this one is a flame graph of it. What does it mean? First, we are talking about samples, but samples of what? Of a call stack. Call stack with the same meaning of the one that you can collect by printing the call stack after an exception or just walking the call stack of your application. And in order to read it, you have to go from the bottom to the top. And indeed, you will read a thread that is calling a lambda, was hidden in the previous slide. But the most important part is that you have A here, that is calling B, that is on top of it, and B is calling C, that's here, and then D. Do not mislead you, the x-axis is not the temporal one, okay? It's just the call stack. The reason why we have C and D with this order on the x-axis is just alphabetical. There are no meaning from a temporal point of view. But let's look together what the meaning behind the width of those rectangles. The width is proportional to the presence of samples, to the amount of samples. That the too long don't read part is that the more a method is seen on CPU and is seen inside the call stack, the more will be larger the rectangle. And it means that if we are looking at this flame graph, we really care about the ones that are larger, obviously. And on top, because A, for example, is very large, but has just B on it, isn't doing anything. And you can see it from here, indeed. But B, for example, is doing some heavy work. And indeed, there is a part in which he is alone on top, okay? And if you see the width of the part in which he is on top, is very similar to C, because both B and C are performing EV work, okay? D, on turn, is twice larger, because it's performing twice EV work. Very simple. This one is the most simplest flame graph we can have in order to understand how it works. But the point is these samples, this call stack, how they are collected. How many people has ever tried the profiling tools of any kind? Perfect, perfect. So you know that there are different type of profilers. There are sampling one, instrumenting one, but as I told you, the FlameGraph is a kind of visualization tool that works at its best with sampling profiler. So we will talk about sampling one. And we will use one that has been in the past in bundle with the OpenJDK. That is JVisualWM. How many people knows about JVisualWM? So many. Makes sense, effectively. So let's see the same program, how it looks like while using a very common visualization way, like the table one and the mixed hotspot ones. And indeed, we see a thread, the same lambda that was hidden in the program, and nothing more. And that's strange. You have to believe me that it is exactly the same program as before. And I was expecting in the hotspot to find A, B, C, D. The point is that they do not exist. So let's dig a little more. Why this JVisualWM isn't showing anything? That's the first problem before looking to get a flame graph from it. EVWork. What it is EVWork? EVWork is a common loop. Isn't doing anything with the array or whatever, and is a for loop using an integer here. This works is a static final that controls how much time is spent inside of it. Okay? It's finished. It's just that one. So in B, C, and D that were performing EVWork, you can just copy this one. Let's see together what happened, given that was the only thing that I have hidden from you. If I change from integer to long, this is the same loop. Oh, JVisualWM works. Incredible. That's strange, no? But now we can check this kind of visualization. So we have the table, we have the hotspot. So let's look together if it makes sense. We have indeed here the call tree. And as we were expecting, we have the lambda A that is calling B, that is calling D and C. And the B was performing some EVWork. And indeed, there is self-time here. Self-time is the time spent inside the method calling instruction of the method itself, so not calling other one. And this same matrix is here, self-time CPU, not self-time. And here we have the total time instead, that include not only the time spent inside yourself, but even calling others. We can immediately see that the samples collected by JVisualWM totally make sense. Indeed, we have B and C that were performing EVWork, and indeed that's the width of the red bar, while D was performing twice EVWork, and indeed we have twice the amount. It's surprising. I mean, there are two ways to visualize the same thing, but the point is, wow, why now it's working, okay? And we can dig together a little bit into how the JDK work in order to understand what's going on. Because we have changed our application in order to make it visible to JVisualWM, okay? This one, I know that many people is trying to read it. Don't read it, it's too long. That's the reason why it's in light gray. I put it just for the record. You can see on the site of the hotspot JDK OpenJDK the glossary of term. And a safe point. How many people has ever heard about it? Nice, it's perfect. It really should be something that is an implementation detail of many JDK, but it's not, because any JDK has it. But I can tell you more. V8 in JavaScript had it. Golang had it. Basically, every managed runtime. That's very important. A save point is a point, a state of the entire JVM in which the JVM can trust, can do its own things. I know that is very simple, very naive as a description, but it's exactly like that. If I want to do something with the garbage collecting, the JVM need the entire application to be at a safe point. It means that the Java thread must be blocked. But it's not something that you can decide as a user. It's an internal mechanism of the JVM. But let's look a little more how much it can relate with this JVisual VM strange behavior. JVisual VM, like many profiler, is using one or together or singularly these two calls. Get all stack traces and get stack trace. These two calls are ones that require your application to be at a safe point. And if you think about it, makes sense, because you need to walk the stack. So if your code is changing, if you're doing something, you can't collect the stack, right? It makes sense. And there are many other operations that require your application to be at a safe point. But the safe point itself, obviously, if you think about it, I told you that as a user, you can't ask the JVM directly to do it. You can use operations that require to do it. And if you ask the JVM through this operation to go at a safe point, how you can do it? I mean, what is doing inside the JVM? When the just-in-time, the compiler, compile your code, your Java code, it injects trap, holes, we can say. That this kind of trap, when a save point is being requested, became active. And if your thread, so your Java code, arrive at that point, then it will block. Okay? When every thread of your application will arrive at its own save point, because each thread has its own save point poll, that's the name of the trap, then the JVM say, okay, we are all together at a save point. Even this part creates some kind of problem if you think about it, because if you have one part of your code that is performing some very heavy work, and the save point poll is right after, it means that it will make all the other threads to wait until it will be at the save point. Because the save point is a collaborative thing. Everyone needs to go there. But everyone needs to go there together. So they have to wait. That's very key for the next of the presentation. But this save point poll, how the JVM decide to put it into your code? What are the heuristics? I haven't listed here all the heuristics, because they are not important. We really care to understand this weird behavior of JVisual VM, okay? So, as I told you, when we have changed from integer to long, that loop has magically appeared, okay? So, the integer loop is called counted loops for the JVM, that specific type of loops. And the JVM never put a trap, a save point poll inside of it. The reason? Because the JVM think that this kind of loop are short by definition, because it is integer, But integer can be even, could be quite big, to be honest. But it's not important. These ones are called counted loop, no save point poll. When a method called by you exit, then it will put a save point poll. So theoretically, that thread can be blocked if a save point request arrives. And when you have an uncounted loop, Which kind of are accounted loop? The one that do not use integer, but to use something more, long. Long is an example. So I think that it's starting to take shape, the idea. No? We have turned from a counted loop into an uncounted loop that contains a safe point poll. So we are giving to our program the chance to be stopped in order that someone, the profiler, will collect the call stack. Okay. There is another thing I want to tell you. I know that are a lot. It's complex indeed, but we will go together step by step. The compiler remove the method exit save points when the methods are being inlined. Being inlined. How many people knows about that? Okay, it's nice. For all the other, I can tell you that inlining is the optimization. Really, because when you have a method that matches a specific heuristic, not very simple to be honest, of the just-in-time, and the just-in-time decide that is a good candidate to be inlined, it means that when you call this method, the body of the method is copied directly into the caller, disappear effectively. And if you think about the save point mechanism, it makes sense that the poll will disappear as well. Because if you think about the getter of a Pojo, okay, the getter of a Pojo is supposed to do something very small. If you make the people that use it to pay the method call and that you can stop each time you request a property from your method, you are saving a lot of chances to optimize that code. It will become anyway, the people won't use get anymore. That would be a win from my point of view, but it's a different stuff. So that's inlining. Inlining means that method exit disappear. Very important. Let's return back to our program. This one is being produced by JITwatch. That's a very nice tool that allows you to have a simpler way to visualize the decision of the JVM related to your program. And it will just use the compilation logs. This one is the same one we have always talked about. We have A that is calling B, that is calling C and D. Okay? In green, we have the methods that are being inlined. So, C, D disappeared, B disappeared, A disappeared. All these methods completely disappeared into this one. The only surviving methods from the decision of the JVM will be this one. About the save point polls. Given that these one were using a counted loop, during the counted loop there are no polls because are short, right? And the method exit save point poll has been removed. So it means that here there are no save point polls. This one is totally invisible to JVisualWeb. That's very bad. And indeed, the only method that has survived is the one that has taken all the blame. Because it's the only one that the get all stack trace can see. If you can't stop your program, how can you check what's the stack trace? It makes sense, but it's very bad if you think about it. Indeed, it's a very, very bad way to play this game. If you are using a profiler, you are supposed to use library or whatever kind of optimized code that use a lot of counted loop. No one will change a loop from int to long just to make it visible to JVisualWeb. It doesn't make sense. And it means the more is optimized, the more you got inlining, and inlining something that you really want to happen, the less the profiler will see it. That's obviously very bad. And indeed, talking about sampling profiler, so the one that are able to collect something that we can see into the FlameGraph, have a couple of challenges that you need to be aware of. One is the save point bias. That is the one we have talked for the whole time, okay? And indeed, it means that the profiler can see anything if the JVM isn't at the save point. The other one is the observer effects. It's something that in a different way we have talked about. I told you that if someone of your threads is very slow to arrive to the save point pole, it will slow down all the other. But that kind of pause in which everyone is awaiting just that single thread is a GC pause. If you enable the GC logs, makes sense that you will find this kind of pauses. Obviously not, because it's not a GC pause. What kind of pause is? I really think that you or any of your customer really want to enable this option in the logs called print GC application stopped time. This one will show the time to enter into a save point, and each time someone is inside the save point and is taking too much time. And then it is the observer effect. Because any profiler that forces your application to arrive each time at the save point, and then, let's imagine together we are using Spring, for example, and you have a call stack of 1,000 of methods. Okay, if you're lucky. And you have maybe 1 million of threads, because we know we have 1 million course machine. And in that case, what would happen? Will happen that the get all stack trace will take time. But until get all stack trace has exit from the save point, your application can't continue. So you are disturbing the application, using a lot of time to stop it, and when you stop it, you will take your time and rest. What kind of effect could have this profiler? Very bad. That's the observer effect. And indeed, we have a right finally to this one. That's a taxonomy of all the JVM profiler types. The first one is the one we have talked about. Get all stack traces one. Very bad, very bad. But the worst thing is that, okay, JVisualVM is free, is wrong. But your kit? JProfiler, the people pay for that. Is recorded. Bad. Okay, let's continue. There are, luckily, ones that work. The point is that you don't have to be save point bias, right? How? Oracle is very smart, because there is one call called async get call trace that belonged to a very old project called Forte. Anyone has ever heard about Forte? Oh, okay, nice one. And not only to Forte, but even Solaris Studios, that despite the name work on every Linux distribution, it's just a better name. And these two profiler allows to call an hidden stealth call inside the JDK that allows to read the call stack without awaiting the save point. It means several good and bad stuff. The bad stuff, obviously, is that if you can do it whatever you want, you can get corrupted stack frame. It makes sense, because if you are calling a JNI function that goes into the native word, where is your call stack frame? The Java one doesn't exist, partially. And in that case, you won't see anything. Indeed, the JMission control is free, but I have a little problem, because every time that a frame is corrupt, it won't tell you. That's another bad stuff. And in the past, it was costing a lot. So it's very bad. Anyway, let's go through the one that really works. The one related to perf. Native tools is not just the only one. Return back to the FlameGraph. Then we will continue with the perf and good profilers. Now, given that I mentioned perf, we can unleash the full power of the flame graph, because getting a flame graph without getting all the information we can get visually, it doesn't make sense just to see Java code, because your Java code is just part of the story. When you run a Java application, you have the GC. GC is written into the JVM through a C++ program, and in a flame graph, you can read it in yellow. And not only the interpreter, the compiler threads, the JVM. Then in red, you have the C libraries. It means JNI. If you are using netty or anything that write to file, read socket, or whatever, they have code written in C, maybe. In that case, you will see it in red. Then you have the orange, because even if you don't want, you have to ask something to the kernel sometime. It means to manage file or whatever, and then you have that too. And then the 2.1, the last but not the worst. You have in green normal Java and aqua Java enlightens. That's so cool, because in my past I always used two separate tools to get all the three separate tools to get all this information all together. I'm using GC logs to understand what's going on in the GC. I use compiler logs to understand what is not doing well the compiler. And then I'm using obviously bad profilers to get the Java part. And we have the all good stuff all together. Obviously, it's a good idea to use it, but it's enabled by using the right profiler. Without it, it can't work. Let's dig together into perf. Perf. When you ask perf to show the sample of your program, what's going on? There is a syscall called perf open or something like that asks the kernel to provide some events. Then the kernel provides a ring buffer to you. How many people have ever heard about ring buffers? That's a queue of event. We can think about it. And then try to fire event through this queue. Then it's up to the profiler to read those events and then collect it in a form that can build your awesome flame graph. What kind of events? The events are, for example, perf sample call chains, records the call chain, the stack trace. So very simple. You ask the kernel give it to you back. But Java, call stack, let's dig together how it works, creating a call stack. It's a very old-fashioned, old-school stuff. We have a three register. One is the instruction pointer that tells you the next instruction of your program that will be executed. And then each time you have a nested call, like before with A that called B that called C, starting from the bottom to the top, you have the stack created for each one of these calls. Arriving to the last one on the top, we have this base pointer that points to the base of the stack that contains the parameter of your methods. Okay? And the stack pointer instead points to the top. There is a convention for many compilers that has been broken so many times that I can't remember, that tell the compiler when create the call stack to record the previous base pointer, because when a method is finished and has to return and you return back, you need to know where to put the base pointer, because you need to point to the parameter of the original method, right? Okay, the fact is that it won't happen anymore. Why is important related to perf? Because perf, in order to give you the call chain, needed to follow this sort of linked list of base pointer in order to understand what was the call stack. But now, in Java, and not only in Java, base pointer is not used anymore. And given that is not used anymore, it's not even created this linked list. So how perf can show you the nice Java call stack? It can't. That's a problem, effectively. Indeed, Brandon Gregg, that is a performance guru of Netflix, has created this patch that allows from Java 8 update 60 to force Java to preserve the frame pointer. It means that when you provide this kind of argument, you are able to ask perf, finally, to get you your methods. It's not that simple, but it's deep enough to let you understand how it works. So it works. Done. Finished. Not really. There are always problems. First one, interpreted code. The interpreted code exists in the JVM. But if you think about what does it mean, the interpreted code, it means that you are emulating all the code inside the JVM itself, that is, mimic this stack machine by reading your code. Effectively, this method calls doesn't exist. And given that they not exist, perf won't show you. That's a problem, obviously. Then you are forced to this specific version, despite what Oracle said. I know many people that are still using 6, Java 6. Legacy programs are everywhere, and it means that if you really want to profile without having the save point problem, because perf is reading the call stack, it won't matter save point or not. It just works. It's very important. And given that having the entire ecosystem before Java 8 is not nice, that you can't profile it. And the other problem is due to inlining, because now you know what it is inlining. And inlining is kind of special. I told you that the method call stack won't exist, right? Because you are copying the body inside the caller. And effectively, there is no call stack. And indeed, given that you have so many inlining decisions by the JVM in your program, probably you won't see many of the most interesting methods. In that case, you should add another option called debug non-save point, that has a very bad name, but remind the save point part, if you think about it, that tells the just-in-time to preserve the debug information while performing the inlining. So the method don't exist anymore, but you have enough information about what the method could be, like the line of code, the bytecode index, in order to allow perf to see what's going on, even if the method won't exist. And I can say that with perf is finished. That's the one that I'm using probably in the last 3 years most of the time. How many people knows about a sync profiler? From tomorrow, really, try it. No, it's so nice. Why it's so nice? We have talked about a lot of stuff. There are the hidden called async get call trace that Oracle has hidden to be used with its own profilers, okay? And this one is good, as I told you, because it is asynchronous, doesn't require your application to be at a save point, and that's very important, it works with Java 6, because Forte is very old. Not old, but it's quite a bit a long time ago. And Java 6 works with it. But it will show you just Java code. That's bad, obviously. So this profiler, so remember the name, sync profiler, is using perf tools to match the stack trace. So you are using async get call trace to get the Java side of the equation. And you use perf in order to understand all the rest. And then you mix together. And you have the perfect profiler. Why perfect? Perfect because it's interpreted code. And it seems stupid, but when your program is at startup, it's very difficult that you get compiled code because it's not hot, it's cold. And maybe you want to improve the loading time of your application. You try with perf, you won't see anything. You try with the sync profiler and you see it because it's interpreted. And this one works, okay? And is open source, that is very nice. And I haven't told you that perf come with at least three different tools in order to arrive and get finally your mixed mode flame graph. And yes, I'm used to them, but I admit that is not very user-friendly. While this profiler is very nice because it allows you to get out-of-the-box flame graph that just work. You just type it and it works, very simple. And it shows very different stuff because flame graphs are not just for CPU time, but for samples. These samples can be everything. And when I mean everything, I mean allocations. I mean which method take more to enter into a lock. It's very cool. And cache misses as well. So we have learned a lot of stuff today related to flame graph, profilers, or whatever. The thing is that the flame graphs are good, as you saw it, are simple, but it's just a matter of taste. You can use table if you want. It's fine. I know it's not a good message after a flame graph talk, but the point is that you need to use the better visualization tool for the things you are doing. If you are just looking at the microservice of 100 line of code, I'm not sure the flame graph is that perfect for that kind of stuff. But the point is that if you try to use the more fancier stuff, but they just don't work because it's a bad profiler, the kind of data are useless, even if are beautiful. That's bad. Finished. I've been very quick. Any question? Please fire away. I know that's late, maybe not, I don't know.
Just could you explain to me what is a corrupted Java frame? Corrupted Java frame.
What's a corrupt Java frame? Yeah, the thing is that when, let me think of one case, for example. The compiler threads in Java construct the Java frame. Okay, they build what will be the kind of calls that you can get. Okay, but when this compiler thread of the JVM will do that work? At a safe point, because they can safely. There is a point in which they can safely change the way in which you execute your code with the new version optimized one. But the point is that if you can collect in always stack frame, maybe you are finding you are racing with it. And in that point, you won't get a properly constructed, built call stack, for example. The one is, and this one is actually an issue. No, I haven't attached it. There is an issue unsolved with any profilers that is related to arrays fill. How many people use it, has ever used it? Okay, you give the array, you give the value to be filled in, and the JVM will do it. If you look at the code, it's just a kind of for loop that do it. But it's a kind of special loop, because the JVM recognizes that, know that you really want to do that stuff, and say, okay, I will replace your bad code with something really optimized that does exactly the same things. The point is that when the JVM does this kind of optimization, sometimes, because the JDK developers are human, like everyone, they have forgot to save the bytecode index of the call, it means that if you try to read the call frame that involves this very optimized version of that call, and you need to understand to which line of code of your program it matches, there is no match because they've forgotten to put the bytecode index. And there is no solution. Array fields is invisible. Incredible. And that's a corrupted frame. And Java Mission Control, in that case, won't tell you that is a corrupted frame. That's very bad. I mean, it's okay that you don't know that. But if you don't tell me that there are 1 million of calls, it's bad. It's not important. Just saying that is a missing information is an information. So please give me that.